Okay, good morning, everyone. So we have been talking about interactions of electronic systems with light. And so there are two general kinds of those interactions. There's absorption of the light. And at the most basic level, the thing we calculate directly from Fermi's golden rule is a rate. Okay, and so the contribution to the rate, or the differential rate, we found is given by a formula that looks like the following. So there's the fine structure constant, a factor of the frequency. So we have some constants out front here, the mass of the electron squared, the speed of light squared. And then we have to do some integrals. And so we're integrating over the direction of the photon and then summing over its polarization. Okay, so this integral is over the direction. And this sum is the polarization of the light. And one thing I wanted to mention is that the sum always has to come inside the integral. And the reason for that is, if you remember your classical electrodynamics of waves, the polarization of one of these waves has to be perpendicular to the direction it's moving. And so here, when you're doing the sum, to know what to sum over, you first have to know what the direction of the wave moving is. Okay, so it has to come inside. And then there were various different ways we wrote this, but one way involves the number of photons present in that
Sorry,
mode.
Professor.
Yes.
Could you please repeat why did you say it has to come inside the integral?
It's because the polarization depends on the direction that the wave is moving.
Oh, okay.
Okay. So this n is the number of photons that are present. If I have my atoms maybe sitting in some bath of photons, there might be lots of those. Okay, and then the thing that comes next is a matrix element that we haven't talked about much yet, but we're going to talk about a lot today. And so this is actually a curly P. This is a vector dotted into the polarization of the wave. And that matrix element appears squared. And then there's a density of states. And then finally, you have to sum over any degeneracies. So this is density of states. And then for each different state that you have that has the same energy, you can have a transition that contributes to the rate. So you should sum or integrate over the degeneracies.
Professor.
Yes.
I'm sorry to disturb you again. Right there, right next to the Ke, is that the same epsilon that's inside that is that the same epsilon that's everywhere else, or is that different?
Yeah, that's the polarization.
No. Right next to that K.
Right next to the K.
The N, the large N, number of photons present.
Yes.
Is that the same epsilon?
That's also the same epsilon, yes.
Okay, thank you, sorry.
Okay. And then this curly P operator, which is a vector, we wrote that down before. That's e to the I k dot r times the momentum operator minus I k cross the spin. Okay, so all of that is for the absorption rate, but that's not often the thing we measure. What we measure might be a cross-section, and we talked about how to trade this for the cross-section, which we call sigma. And so there's just some constant of proportionality there that one has to include. So that was for absorption, and then for emission, the formula can be written in also very similarly. So by the way, you can also trade the number of photons for the intensity of the light. There's different ways of writing these formulas. Okay, so for emission, it looks very similar when you write it in terms of the rate. It's got the same prefactors. You again have to do an integral and the sum over polarizations. But now what goes here, we showed last time, is the number of photons present plus 1. Okay, and the number of photons present contributes to what we called induced emission. It's induced by the photons that are already there. And the plus 1 is spontaneous. That's going to contribute even if there are no photons present. You can have an excited state that emits a photon to go to a lower state just because. Okay, and then there's a matrix element, which is the same matrix element basically, except we take the Hermitian conjugate of what's inside. That came out of Fermi's golden rule. And then the same density of states. It's always the density of final states and the degeneracy of final states that you're summing over, because those are the different things you can end up in. Okay, and just as a reminder, the only thing we were actually able to calculate here was this part. And then Einstein's indirect argument told us that the spontaneous part must be the plus 1. Okay, so today we're going to concentrate on what we haven't talked about much up until now, and that's the matrix element part. And specifically, we're going to start with an approximation, which is often a good approximation, called the dipole approximation. Okay, and the dipole approximation is where you assume that the wavelength of the light that you're emitting or absorbing is much, much larger than the size of whatever electronic system you're talking about. I'm going to say atom. Okay, so before using that, let's see why this might be a good approximation. So if I have the wavelength of the light, that's 2 pi c over omega. And now I'm just going to multiply top and bottom by h bar. So the reason for doing that is now h bar omega and the denominator is the energy of the photon. And that's useful to keep track of because the energy of the photon is always equal to the energy difference between the two states. So as long as I'm only worried about orders of magnitude here, I can just replace that by the typical energy of any given state, because the difference in energies will be comparable to that. And so for an atom, it's the atomic number E squared over the expectation value of the position operator, right? Just roughly. So we got that, for example, for hydrogen-like atoms. And so if I simplify this a little bit, the typical size of the atom is in the numerator divided by the atomic number, and then E squared over h bar times c is also known as the fine structure constant. So all of this is saying that this will be valid provided that that denominator is very small. Then the wavelength of the light will be much larger than the size of the atom. So that means z times alpha should be much, much less than 1. And since alpha is a famous number that's 1 over 137, that means this is valid for the atomic number much, much less than 137, which is, even when Z is much larger, it turns out the dipole approximation works better than you might think. Okay, so if the wavelength of the light is very large, then that means K is very small. So we're going to assume that for a while. So if K is very small, then e to the I K dot R, which is appearing in our operator in the matrix element, is approximately just 1. This is true over the size of the atom. And that's all we care about, because when we compute the matrix element in position space, we're going to be basically integrating over the atom. Okay, so if we go back up to our operator here, that's telling us we can just replace this by 1. And then the other thing we're going to worry about right now is the K cross spin part of it. And we're going to argue that also can be neglected. Okay, so also spin is negligible. It's not always true, but it's true in our approximation that we're doing right now. And so to understand that, let's consider the relative magnitude of K cross S divided by the momentum, which is the other term. Okay, so that's K times spin is h bar over 2 in magnitude. Okay, and in the denominator, the typical momentum is h bar over the size of the atom. Okay, and the reason for that is the uncertainty principle, which says if you know the size of the atom, or if you know that you're within the size of the atom, then your momentum is in some range that's comparable to 1 over h bar times that, or h bar over that. Okay, so then we can write that as, using the relation between K and omega, this is omega over C times the typical size of the atom, which is otherwise known as the typical size of the atom divided by lambda. And that's what we're assuming is very small. Okay, so within this approximation, our operator P vector curly K is just equal to the momentum operator in the matrix element. Okay, and so in particular, that means when we wrote this down within our approximation, let me include my polarization vector in there. This is the polarization vector dotted into this matrix element. All I have to know is the matrix elements of the momentum operator. Okay, but it's going to get even better because now we can evaluate this using a trick. And the trick is going to be notice that the momentum operator is the commutator of the Hamiltonian with something. In fact, that something is the position operator. So let's write that down. We're taking the commutator of the unperturbed Hamiltonian with position. Let's just write down what the unperturbed Hamiltonian is. So I'm including here some potential that might, be the potential that binds my electron to the nucleus. That's really an electrostatic potential. But the important part of it is that it's not part of the electromagnetic wave, which is coming along to hit this thing. That's why we're including it in H0. And we're taking the commutator of that with position. And so if you stare at this, you realize, aha, this is not going to contribute because any function of position commutes with position. Okay, so this doesn't contribute. And so the only part that contributes is the commutator of p squared. with position. And we know how to evaluate that. This is minus I h bar over the mass of the electron times P. So that means whenever we see P in our matrix element here, we can replace it by the commutator of H0 with position with 1 over that factor put in there.
Professor,
Yes,
that 1 over 2me can come out.
sure, it's not an operator. It's just a number.
But that doesn't mean it's being multiplied by both of those?
It's being multiplied by P squared. But it's just a number. It's right. If I have 7P squared, I calculate the commutator, I can just pull out the 7. Is that your question?
I thought when you pull it out, it's being multiplied by both the P squared and the R. That's why I thought maybe.
No, so it's only included once.
Oh, okay.
If I put it on both, then I would have that number squared.
Okay, thank you.
All right, so what does this mean? It means when we see this matrix element, okay, now I put our factor of I m sub e over h bar times polarization vector dotted into what I've replaced it by, which is the commutator of Hamiltonian with position. That's a commutator. And so why are we doing this? We're doing this because we know how the unperturbed Hamiltonian acts on the initial and final state. So we can just replace it by its eigenvalues. Because no matter which term in the commutator you look at, it's either hitting the final state or the initial state. And so when you work that out, this is I m sub e over h bar, initial or final state energy minus initial state energy times F polarization dot R. Okay, and now, even better, we recognize that the difference in energies divided by h bar has to be omega. That's what the delta function in the golden rule told us. And so this is I m sub e omega, final state, position operator in the polarization direction, that's what that dot product is telling us, times the initial state. Okay, so plugging that into our bigger formula, let's say for the cross section for variety, the cross section for absorption, and I'm going to write here dipole because we're in the dipole approximation, is 4 pi squared alpha h bar omega. The m sub e's cancel. We have our matrix element squared, and then we have our density of states factor. Okay, and more generally than that, in all the different versions of this formula, like for the rate or for the emission, so more generally, in this approximation, we get to replace the matrix element squared by the mass of the electron squared, the frequency squared, times the corresponding matrix element of position instead. Okay, that's for any kind of electric dipole absorption. I threw in the word electric there because it turns out there's also magnetic dipole, which we'll get to soon, which is a little different. Okay, and for electric dipole emission, so emission you do almost exactly the same thing. It's just that now your polarization vector gets complex conjugated, which is mostly important if you're talking about circular polarization where the polarization vector is complex. All right, so let's specialize to the case of spontaneous emission. So there, for example, I could ask you for homework to calculate the rate for the n=2 level of the hydrogen atom to spontaneously emit a photon and go to the n=1 level. Maybe I even will ask that. Okay, for spontaneous emission, the remaining hard part of it is to sum over and integrate over the k's. So we must sum over our polarization vector complex conjugate, which must be perpendicular to the direction the wave is moving. So to understand how to do that sum, let's temporarily fix the direction the wave is moving, even though it can go in all possible directions. So let's temporarily fix the propagation direction of the wave to be z hat. And then our two polarization vectors that we can have are x hat and y hat. Okay, and so if we do our sum over polarizations of our matrix element squared, that's just fx initial squared plus fy initial squared. Right, because this is just, when it's x hat, that's just saying let's take the x component, and when it's y hat, we'll take the y component. Okay, so that's what we get in the special case that k hat is along z hat. But next we need to integrate over all possible directions for k hat. So now need to integrate over all angles or all directions for k hat. And so let's write down what that must equal. We're doing an integral d omega k hat, inside of which there is a sum over the two polarizations that can contribute. But now we know at least what it's going to look like for z hat direction. For any other direction, there will be two components of the vector that will contribute, like x and y did here, out of the three possible components that there could have been. There could have been x, y, and z, but there was actually only x and y. So when we do the integral, we're going to get a 4 pi from the angular integration, but then we get a factor of 2/3 because 2 out of 3 of x and y contribute. But on average, it's all three things, right? So by putting in the 2/3, we're taking into account the fact that only 2 of the 3 polarizations in any given situation can contribute. So that's a standard argument. If you want to, if you really want to, you can just actually do the integral, but it's a little bit more unpleasant and it gives the same answer. So this is equal to a factor of 8 pi over 3 FRI dotted into, when I take the complex square, I'm taking the complex conjugate, so it looks like this. Okay, so now if we can calculate just the expectation value or sorry, not the expectation value, the matrix element of the position operator vector between the two states. Then we dot it into itself complex conjugated and include this factor of 8 pi over 3. And now we're done with doing the integrals and sums. So if we put this into the formula for spontaneous emission, so put into formula for gamma emission spontaneous. So that's again a rate. It's a number of transitions per unit time. And we get this I goes to F plus H bar omega is a relatively simple formula. 4 times the fine structure constant, omega cubed over c squared. Omega we're going to know because it comes from the difference in energy between the two states we're talking about. And then we just have to calculate this thing. Okay, so that's a relatively simple formula to calculate. I want to emphasize this is all in an approximation. This is the electric dipole approximation for this. And the other thing to emphasize is that when you do this, you're really doing a vector matrix element squared. So the bad news is you actually have to compute 3 matrix elements and then dot them into their complex conjugate. So it literally means this right here. The bad news is you have to calculate 3 of them. The good news is that in many, many situations, some of those 3 will vanish. And so to save yourself heartache, you want to decide ahead of time which ones are going to vanish and not spend a lot of time trying to calculate them when in the end you're going to decide that they vanish anyway. Okay, so we'll actually talk about that in just a minute, but first I want to say something more about the interpretation of this gamma. So we can talk about the lifetime of an excited state. It's related to this gamma, as we're about to show. So to define it, let's let the number of atoms in the initial state be some number that we'll call n sub I. Let number of atoms in the state I, that's the initial state, be n sub I. And let's ask how many at some time t. And let's ask how many atoms there are a little bit later. So if we evaluate n sub I at t plus delta t, it's going to be the number we started off with at time t minus delta t times the rate. But that's the rate for one atom to transition, and therefore we have to multiply by the number of atoms there are, which is n sub I. And this gamma here, it's important, is going to be the sum over all final states of the individual rates. So you can't just put in one of them just because that happens to be the one you calculated. You have to somehow calculate all final states and include all of them in summation in there. But let's say you can do that. Or let's say you've calculated the biggest one and the other ones aren't so important. Then by simple algebra, we can rewrite the situation like this. Okay, that equals minus the rate for the state I in times the number I. And the good thing of writing it this way is that that is the, in the limit delta t goes to 0, that's the derivative of n sub I. And so what have we learned? We have a differential equation for the number of atoms present as a function of time. It just equals this summed rate times the number of atoms. And that's a great differential equation because we can write down the solution relatively easily. This is the number of atoms present at some initial time times e to the minus t0 times gamma sub I. Okay, and so it's that sense in which this is this is related to the lifetime. So the lifetime defined to be the time needed to decrease the number of atoms by a factor of 1/e. That's different from the half-life. The half-life is a factor of 2. So this is one way of defining the lifetime, is equal to nothing other than 1 over the gamma. Okay, so if I calculate the gamma for all possible final states, add them up, take the reciprocal, that will be the lifetime of my state. And so states that have large gammas don't live very long, which is often the case for excited states of atoms. Okay, questions on that so far? All right, so now we're going to talk about, we're not going to worry so much about specifically evaluating the matrix element, but we're going to be just interested in when does it vanish? When do we not have to worry about it? And that's given by electric dipole. And the jargon for this is often because we don't want to write electric dipole or say that many syllables. We just call it E1. So there are selection rules that tell you when it vanishes. Okay, and so what we're really asking here is, when does this matrix element vanish? Because if it does, we don't have to compute. So it's very often the case, especially when you're talking about atomic transitions, that your initial and your final state are actually eigenstates of angular momentum. And then that makes it easy to answer this question, or relatively easy. So suppose our initial and final states are eigenstates of angular momentum. We already know they're eigenstates, or they're supposed to be eigenstates of the unperturbed Hamiltonian. So as well as in order for this to be true, our unperturbed Hamiltonian better commute with angular momentum, but it often does. So now we can answer this question just by recalling something that we proved last semester, or some things that we proved last semester. And so this is proved in section 10.4 of the notes. Is if I'm calculating a matrix element between two angular momentum states of the position operator, that's 0 unless the difference in the angular momentum quantum numbers is plus or minus 1. Notice 0 won't work. It's got to be plus or minus 1, one of those two. We did that selection rule by doing a double commutator, you may remember. Okay, and then more specifically, I can ask about different components of that. So for example, the reason I'm mentioning the different components is in some sense they're easier to understand than the general one. This is 0 unless m prime equals m. So one way of knowing why that's true is just think about this in terms of the spherical harmonics. And so when you calculate this thing, you're doing an integral d phi, and then you get an e to the minus m prime phi. That's from this thing. And then from this thing, you get a factor of e to the I m phi, and z in spherical coordinates doesn't depend on phi. And so this will be proportional to, so this will only be non-zero when m prime equals n. Otherwise, it cancels and gives 0. And then similarly, you can do interesting combinations to look at are x plus or minus iy. That's 0 unless m prime is m plus or minus 1. So if you have just x, then x is a linear combination of x plus iy and x minus iy. So that will be non-zero if and only if m prime is either m plus 1 or m minus 1. And again, the reason for this you can see from the spherical harmonics rule. So again, the final state has that factor, and the initial state has a factor e to the I m phi. And then the x plus or minus iy has a factor e to the plus or minus I phi. And so the bottom line is we have all these rules that tell us that we don't need to bother trying to compute it unless these are satisfied. Right, so what you don't want to do is write down a big, huge integral expression and then only much later realize, oh, this thing just vanishes. It just vanishes just because of the phi integration, maybe, for example. Okay, so for an electric dipole, an E1 transition. And so first we're going to consider the case where we only involve one electron. So one electron is transitioning from one state to another. Then what I just wrote down tells us delta L is plus or minus 1. Delta M sub L is 0 or plus or minus 1. Here I'm taking into account both that and that possibility. Okay, and then the other thing is that none of this R never changes the spin. It ignores the spin. It doesn't have anything to do with spin. That means the Z component of spin can't change. Okay, and as a corollary, by the way, of the first one, we learned something about the parity. So also, the parity eigenvalue, which we've been calling pi, of the final state has to be minus the parity eigenvalue of the initial state. So this is parity. And remember, the only possible eigenvalues of parity are plus or minus 1. So this is saying whichever parity the initial state had, the parity of the final state has to be opposite. Okay, and the reason that follows, that's not an independent thing, it's a useful thing, but it follows from the fact that the parity of an angular momentum eigenstate is just minus 1 to the L. Okay, so that's the E1 selection rules, E1 transition selection rules, if you only have one electron. But then remember, we had atoms that had multi-electrons, where things look almost the same.
Is this section 16.4 of the notes?
Beats me.
Huh?
Could be. I don't know. I don't have the notes in front of me at the moment. Let me look. Yep, 16.4. Okay, so for multi-electron transitions, basically you're just going to use the total angular momentum instead of just the orbital angular momentum. And that can make a difference because that combines the individual angular momenta. And so now what you get is delta J is 0 or plus or minus 1. So there's an extra possibility in this case. Instead of just delta L equals plus or minus 1, you can have 0 now. I'll explain why in a second. But the rest of it looks very similar. So the change in the J Z component is again 0 plus or minus 1. The parity again is the opposite for the initial and final states. And then finally, I'll talk about this in a bit. This rule basically says you can't have both the angular momenta be 0. So I'm saying the sum of them is greater than 0, which means since neither one can be negative, that means they both must be greater than 0. Okay, so let's talk about why these are true. The first two are true because the photon carries angular momentum 1. If you think about the photon as a particle, which by the way is not obvious at all from the way we treated it classically, it carries angular momentum 1. That's its intrinsic angular momentum or its spin. And so now if I take the angular momentum in the initial state and compare to the angular momentum of the final state, tensor product with 1 for the photon, okay, that can be JF plus 1, or it could be JF, or it could be JF minus 1. But those are the only things that occur in the tensor product of something with angular momentum 1. And so that's where this rule comes here. And then this rule just comes from the Z components of that same statement. Okay, this rule is the reason for it is it's a parity selection rule that we studied in generality way back in section 4.2. In fact, the end of section 4.2. Okay, and that didn't necessarily have anything to do with transitions or anything else. It was just a matrix element statement that if you calculate a matrix element of any operator at all, that's 0 unless the product of the parities of the states and the operator is 1. And for us here, the relevant operator is the position operator, and that we know has parity minus 1. Right, so right away that tells us the initial state and the final state have to have opposite parity so that when we multiply by minus 1 here, we're gonna get plus 1. Okay, and then finally there's this last one, this last selection rule. And that one's a little bit sneaky because it's actually always true. It turns out it doesn't have anything to do with the electric dipole approximation that we've been making. Okay, so the J initial plus J final greater than 0 rule is completely general. Maybe I shouldn't say completely general, because what I mean by general is this is for all 1 photon transitions. So you can have as many electrons as you want involved, but only 1 photon. And so to restate it, which will make it clearer why it should be true, you can't have a J equals 0 state going to another J equals 0 state plus a photon. Okay, and the reason why is, here's my j equals 0 state, spherically symmetric. Here's a j equals 0 state, spherically symmetric. Here's a photon wandering off in some direction. And if I just look at the components of angular momentum, since j equals 0, it's certainly true that the z component is 0. Same thing for this. But photons always carry plus or minus 1 unit of angular momentum, not 0. Okay, that's just a feature of photons as particles. And so there's just no way that that can match up. And it doesn't matter what approximation you're working in. Okay, so now we have this second set. This is a more general set of selection rules. Okay, and so if something violates those selection rules, it's called forbidden, which is a sort of a tricky terminology because it doesn't actually mean forbidden. That's just the word we use. So if the above E1 selection rules are violated, it's called a forbidden transition. Okay, but not completely, because it's only forbidden within the approximation that we made. Nevertheless, the jargon is that it's forbidden. So there are ways around it. Here are two big ways around it. Ways around it being forbidden. One is you can just emit 2 photons. But then the rate's going to be much smaller. Okay, so I have 2 photons coming off from my state. Another way around it is you can use the non-p part of our total p operator. Okay, so both of those give a low rate. So we're actually already familiar with a forbidden transition that is actually taking place all the time. So example of forbidden transition. And that's the 21 centimeter line that we've talked about several times. That's a hyperfine, a transition between 2 states that are split by the hyperfine interaction. And remember, that involves the spin flip. And so the easiest way to see that it's forbidden by the selection rules is because it flips the spin of the electron. That means, and there's only one electron involved because it's hydrogen. That means the change in the m sub s quantum number is not 0. That violates the selection rule, but it still happens. It's just that it's not an electric dipole transition, and so the rate is highly suppressed. But space is very big and very cold, and so if you have regions of space where there's nothing but hydrogen around, and there's lots of it out there, then even though it doesn't take place very often, it's the only thing going on, and so that's what you see. Okay, so let me just say one more thing about what happens when you go beyond, and we'll talk about this more next time. If you go beyond the electric dipole approximation, and so next time we'll identify the part of this that is in fact responsible for the 21 centimeter line. All you do is you expand your e to the I k dot r factor for small k. Okay, and so I'm not going to, the details of this are in the notes, but here's how it works out to the next order. So the first order is just what we had for the electric dipole, E dot P. The second order looks like this. It involves both the angular momentum operator and twice the spin operator. And then there's a funny part that looks like this. K dot R polarization dot P plus K dot R, these are actually K hats, K hat dot R polarization, sorry, that's K hat dot P polarization dot R. Okay, and those are just the first terms in the expansion, and it goes on forever. Okay, so this is the E1 part. This part right here is called magnetic dipole, so it's called M1. And this part right here is called E2, which stands for electric quadrupole. And then there's magnetic quadrupole and electric octupole, and on it goes. The idea, though, is that the one that will contribute in any given situation is the first term that you encounter when you do this expansion. Okay, so next time we will talk more about that expansion and talk about the selection rules that apply for each of these different kinds of transitions. All right, any questions on today's lecture?
Professor, midterm is Monday, correct?
Good, yes. So the midterm is a week from today. And next time I will have more information about that. But basically, other than the subject matter, it will be the same deal as last time.
So how many pages can we bring with us?
It'll be the same as last time.
4?
I think I said, yeah, 2 front and back, so 4 single.
Okay.
Whatever I said last time, it's going to be the same deal. The subject matter will be different, and it will not be. You should not consider it as cumulative in that sense. It will be since the last midterm, which is not that many homework sets. Okay. All right. Any other questions on today's lecture? We'll talk about the midterm more next time. All right. In that case, I will see you on Wednesday.